Hi there, I found this little guy on eBay at a very reasonable price, probably because it's not in very good shape. It's an AC microvolt meter of type TM3A made by Level. As you can see, it covers 500 volts down to 15 microvolts full scale and should go up to 3 MHz. There's rust everywhere on the enclosure, but it's particularly bad at the rear. Let's see if it can be rescued. The rear panel is held with 4 screws that have to be removed. Once that is done, the panel can be lifted out. Clearly the rust came from the inside at this corner, and it's quite obvious what happened here.
Battery leakage.
The battery in question is one of these, a 9V PP9. This one is from the Marconi TF2700 bridge, where it caused a similar mess. I don't have a spare PP9 battery handy, so for a first test I just connect the battery clips to my bench power supply. From off, the first position of the switch is a battery test. The needle goes rather slowly, but it ends in the OK field for the battery. I'm using exactly 9 volts on the bench power, so obviously they prepared for some slightly higher voltage than 9 volts with a fresh battery and for slightly lower voltage later. Moving on. Wow, what's going on? Some full deflection at 500 volts, but it comes down soon enough. Same thing for 150 volts, but less severe. The input connector on this meter is a type that I'm more used to see on antenna ports, and in a crunch I could use alligator clips to connect the outer and inner ring, but I do have a BNC adapter for this, allowing me to connect coax cables with BNC connectors. I'm applying a sinusoidal AC voltage of 1 volt RMS at about 400 Hz, as you can see on the multimeter on the left. Apologies for the glare. The TM3A repeats the wild swings as I downrange to 5 volts. And after it comes down, the needle is roughly at the 10 on the lower black 0 to 50 scale. That is looking promising. Going to the 1.5 range, it right away moves to the 10 on the uppermost 0 to 15 scale, but then settles at a slightly lower value of 9.5, meaning of course 0.95 volts. Some cal is probably needed. Dropping the input by 20 decibels, so 1/10 of the voltage or 0.1 volts, and moving the range switch by 2 positions to the right, the TM3A is now 20 dBs more sensitive, so the needle should be exactly where it was before, and it is. This is a good sign. Repeating the same game, dropping the input by 20 decibels or a factor of 10, and now the multimeter definitely needs to be put into the millivolts to give a sensible reading. Moving the TM3A switch by 2 positions to the right to the 15 millivolt range, and again the needle is where it was before. And another repeat. The 1 millivolt signal is now so weak that the multimeter is struggling. Not so the TM3A, which can still show and even has 3 further ranges in reserve. Back at the 1 volt signal level at 400 Hz, let's change the frequency instead. I'm using an analog oscillator as source, which delivers a very clean sine curve, but its frequency has to be hand adjusted. Anyway, about 4 kHz, and there was just the tiniest bit of movement on the needle. The analog source is in fact dropping the signal momentarily while I change frequency, so the important part is not that the needle moves, but it goes back to the same position. At 40 kHz is now a little further to the right than before. That may also be a problem of the oscillator. The multimeter isn't very accurate at this frequency. Going to 400 kHz and the multimeter is showing 0 because its maximum is 100 kHz. The TM3A is still going strong. Is it worthwhile spending any time on restoring? And yes, I think it looks quite promising. I need to get rid of all the leaked battery goo and rust and strip the enclosure bare. So the first step is to remove the front plate. After removing the 4 screws, the whole thing comes right out with the PCB and all. Everything is mounted to the front plate. The PCB looks a bit messy compared to modern standard, with its components going ever which way, sometimes elevated, sometimes crossing each other, probably all to get optimum high frequency results, and many electrolytic caps. Attention to detail, the red output terminal is shielded from the input attenuator. Trimmer capacitors at the attenuator, which is all hand soldered point to point. I have no video footage of the actual cleaning as most of it happened outside. These were the steps. I removed everything that was removable from the unit. The screws, nuts and so on were all left in a small jar with W40 in it. Removing the rust using a wire brush by hand to minimize the dust generated, and later, after the bulk was out, with a Dremel and a wire brush bit. I then put on gloves and washed the whole thing thoroughly and let it air dry. For paint I went with Hammerite Blue Hammered. I could not get the same tone as the original, so I had no choice but to paint the whole thing, even at places where the original paint was still okay. I did the whole painting outside because of the strong smell of paint. I then left it for a week in the garden shed to make sure most of the paint smell had dissipated. Here's the result. Now, I'm no expert in painting and there are definitely flaws, but I can live with that. This is the box before all the hardware was back installed. And this is it with the hardware back in. Handle, feet, tilting pail and so on. I did add an extra battery clip for a standard 9V battery, which I will use for now. I want to keep the option of using a real PP9 like I did on the TP2700 video, or maybe, as some people suggested, a hollowed out PP9 with 6 standard rechargeable AAs inside. I tested the current draw with my multimeter at 9V, and yes, the TM3A still does its wild swings initially. This goes away when the meter has been running for a while and is in fact normal and stated in the manual. The draw is between 3.5 and 4 milliamps. Definitely a standard 9V battery can handle this. The battery, this one is rechargeable, is held temporarily using cable ties. It's possible to change the battery by sliding it upwards. Not terribly elegant, but it works. The schematic of the instrument. This one is for the TM3A and the TM3B, which are the same basic unit, but the TM3B has an additional bandwidth limiter to get rid of unwanted noise. There's the input with a complex attenuator followed by a multi-stage amplifier. The output of the amplifier is accessible at the 2 sockets at the front. From input to output is a gain of 70 decibels. The nominal output level is 150 millivolts. This provides a handy voltage amplifier from 1 Hz to 3 MHz. The rest of the circuit rectifies and drives the meter. There is sadly no diagram of the PCB or a list of components. The yellow annotations are mine, assigned arbitrarily when I tested the capacitors. You already noticed that there are an amazing number of fairly large capacitors in this unit. The same annotations on a picture of the PCB. It is not complete. I tested all capacitors and they were all still good. I was tempted to change them anyway, but some are tricky, like this one, which is mounted elevated and has a coil of 1 winding going around it of sorts. Some high frequency magic, I suppose, and as long as it works, I decided to leave the PCB alone. One last remark on the PCB. The diagram in the service manual shows that the gain trim pot on my PCB was replaced by fixed precision resistors mid-1978. Since my TM3A has that trim pot, it was made latest mid-1978, possibly way earlier. It is therefore at least 46 years old as of the making of this video. Anyway, on with the calibration. The first thing the service manual wants you to do is to adjust the gain of the amplifier by applying 12.5 millivolts at 1 kHz and with a range switch set to 15 millivolts. Verify that the output is 125 millivolts plus minus 3 millivolts. Well, since it's just 0.7 millivolts off, that is still spot on, no need to mess with it. I notice, however, that the meter dial was a little below the expected 12.5 on the top scale, so that will need adjustment, but that comes later. The last thing on the amplifier section is to adjust the bias so that one gets less than plus minus 50 millivolts DC on the output. Again, with just 0.7 millivolts, there was nothing to do. This amplifier is doing fine. The next section in the service manual has me baffled. I'm supposed to set R in, which is this trimmer here, so the meter represents an input resistance of 9 megohm at 200 Hz in the 50 microvolt range. Okay so far, but then to test this, I'm supposed to put a signal in that drives the amplifier output sockets to 500 millivolt and then take the measurements at these sockets. What measurements apart from the 500 millivolts, please? And how am I supposed to judge from that on the input resistance? The service manual is silent on any of these questions, as this paragraph is all there is for instructions on this adjustment. My best idea was this. I connect the generator at 200 Hz through a 9 megohm series resistor to the meter. When the switch is in position B, the resistor is shortened, so the generator voltage goes directly to the TM3A. I adjust the generator so the TM3A amplifier output gives me 500 millivolt. According to my calculations, that should need a generator output voltage of just below 160 microvolts. Anyway, I then flip the switch to position A, so the 9 megohm resistor is now in series with the input resistance of the TM3A. Together, the two 9 megohm resistors form a divide by 2 voltage divider, so the amplifier output should drop by half to 250 millivolts. If it shows less, then the input resistance is lower than 9 meg. If it shows more, then it's too high. The problem is that the generator voltage of 160 microvolts is so low that breaking the shielding to insert a resistor, let alone a switch, introduces so much noise that the measurement is impossible. I had to up the whole thing by a factor of 10,000, which is this setup. I feed enough voltage so that the amplifier output is 150 millivolts. Then I introduce a 10 meg series resistor. Apologies for the blurriness. And the amplifier voltage and readout drops as expected, but by about 2/3 rather than half. Okay, I used a 10 megohm resistor, so a little below half would be correct, but this massive drop shows that the TM3A input resistance is more around 5 megohms, not 9. I am suspecting that my measurement method is not what Level has in mind, so I decided to leave R in and C in. C in does a similar thing for the input capacitance, well alone for now. If someone knows what the correct procedure is, please leave it in the comments. A word from the future. The input resistance is not the only place where the service manual could have been improved or made clearer. I read this as that the calibration was supposed to use 125 millivolts at 1 kHz, but no, it is using 125 millivolts minus 10 dB, which is only 39.5 millivolts. I only recognized the fine distinction on where the comma is when I worked on the video, which was a week or two after I had made the calibration in the 150 millivolt range, because clearly with 125 millivolts the meter would overload in the 50 millivolt range. Also, labeling the adjustment pots 40 dB, 80 dB and gain is not helpful. Instead, they should have been labeled in accordance with the voltage range each covers, which I have done here. So here I mistakenly applied 125 millivolts at 1 kHz and not 125 millivolts minus 10 dB. And since the only range suitable for this is the 150 millivolt range, I adjust the meter here with a trim pot meant for the 50 millivolts and lower range. Adjusting the wrong pot did however change the needle position because, as the manual states, the low range adjustment do influence the higher ones, which is why they needed to be done first. I tested the adjustment of the lower ranges by successively dropping the signal level by 10 decibels and following with a meter range switch, which, as you can see from the red labeling, is in 10 decibel steps. The net effect is that the needle should always show the same reading, which it does. So despite doing it wrongly, the low ranges are in fact calibrated okay. With this setup, I could not go down to the very lowest ranges because the attenuator in my signal generator does not support lower voltages. But as you can see, when applying 1.5 volts in the 1.5 volt range, the mid-range readout was definitely too low. I used the 40 dB trim port to adjust that, but of course at that time I did not realize that this trim port is also the one for the 150 millivolt range, which I had just calibrated. And then I used the 80 dB trim port for the adjustment of the high voltages in the 15 volt range, which was also reading too low. But because of my earlier error, I had to repeat the whole car, this time starting at 50 millivolts instead of 150 millivolts, but I did not video this as it's pretty much a repeat, but after it was all over I ran a test over all ranges. Starting at 1 volt at 1 kilohertz in the 1.5 volt range and using two attenuators in series. One is in my signal generator and the one that you see here. 1 volt is shown as 10 on the upper scale, so all is good. Lowering the signal by 10 dB on the attenuator and then lowering the range to 500 millivolt gives the same needle reflection as expected, but what we are really seeing is 316 millivolts on the lower black scale. This continues now. 10 millivolts in the 150 millivolt range, 31.6 millivolt in the 50 millivolt range, 10 millivolts in the 15 millivolt range, 3.16 millivolts in the 5 millivolt range, 1 millivolt in the 1.5 millivolt range, 316 microvolts in the 500 microvolt range, 100 microvolts in the 150 microvolt range, 31.6 microvolts in the 50 microvolt range. I have to use the attenuator on my function gen for the last step. 3.16 microvolts in the 15 microvolt range. Pretty impressive. Now for the higher voltages, starting at 3.16 volts at 60 Hz in the 5 volt range. I'm trying to maintain the same stepping, although I don't have a convenience of a step 10 dB attenuator now. 10 volts in the 15 volt range, 31.6 volts in the 50 volt range, 100 volts in the 150 volt range, 316 volts in the 500 volt range. All reasonably accurate, and for this being a relatively simple meter, pretty good. I did run a proper bandwidth test after the calibration, and here's the result. There is some weirdness going on at the very right, but that's way out of the specification range, so can be ignored. Since I was using 1 volt RMS, the first line in the spec applies, which means plus minus 3 dB up to 3 MHz. There is this little dip here between 1 and 4 MHz, but it's just a 1 dB drop on an otherwise nearly flat line, so well in spec. Up to 1 MHz it should be within plus minus 0.3 dB, and the worst part here is plus 0.2 dB, so also well in spec. I must say I'm quite impressed by the TM3A. It delivers very good results with a fairly simple design. If you are on the lookout for an inexpensive microvolt AC meter, the TM3A or B are worth a look. If you enjoy my videos, don't forget to like and subscribe. There are many more projects, repairs and reviews coming up, and it would be great if you decided supporting this channel by becoming a Patreon. Thanks for watching.